Okay, and logarithmic coordinate. What is that logarithmic coordinate? So we have omega in the x-axis and dB decibel in the y-axis, right? So this is the standard representation of decade. Decade means DEC, that is the notation for this decade, is equal to log of omega 2 divided by omega 1 base 10. And octave also we can represent in terms of octave. Oct is equal to log of omega 2 divided by omega 1 base 2. So in whenever we represent the signals here, we can represent in terms of decade or octave. So decade, this is the standard formula, base 10, log base 10. And here for octave, this is the standard formula, log base 2. So the gain magnitude, this formula you have to remember. There is no shortcut for this. So the gain magnitude is many times expressed in terms of decibels. Mostly we represent the magnitude of the signals in terms of dB. So this is the standard and very important formula. You have to remember how we are calculating this value. So dB is equal to 20 times log of A base 10. Where this A comes from, A is the VO divided by Vin. This is the transfer function. The output magnitude divided by input magnitude, that is equal to A. So if you multiply this A by this 20, and also you have to make this log of this A with respect to base 10. Then you will get this dB. So in the filter analog filter studies, we had seen the low pass filter frequency response. So in the y-axis we have always in terms of dB, right, minus 3 dB and so on. So how we calculate that dB value? So we use the transfer function, or the transfer function, so we have to make this log value and then multiply by 20. So here you can see where A is the amplitude or gain. A decade is defined as any 10 to 1 frequency range. Any 10 to 1 frequency range that is usually represented by decade. Decade means normally it's called 10. So you know, the last decade I was in another country, something like that. So last decade means 10 years ago. So decade, we call that, we also use this in our normal vocabulary. But in electronic industry, in mathematical analysis, it means the same actually. The decade is defined as 1 to 10 with frequency range. Here now we are talking about with respect to frequency. And octave is 2 to 1 frequency range. So 20 dB per decade is equal to 6 dB per octave. So if you want to equate this and this is the formula. But I want you to remember, so everything is just general knowledge, but you must remember this part. Let me change my pen color. So dB, you have to use this formula to calculate dB from the magnitude. This one you already know, transfer function, and the dB is equal to 20 times log of A base 10. Bode plot construction. So Bode plot construction, we will see just for an example, a few cases. Maybe we will see 5 cases. This is the case 1. If you have a constant in the transfer function, what will happen? Y of s divided by R of s is equal to k times s plus z1, s plus z2, and so on. And in this is the numerator, and denominator we have s plus p1, s plus p2, and s square plus as plus b. So this is the mathematical representation of one electronic system's output response. We assume this is the output response. So now here you can see we have the magnitude. So k, now we have to find the value of k in terms of dB. So what is the formula for that? We already know here. 20 times log of A. So 20 times log of K, this log modular K in dB. Of course, the base is 10. And the phase angle is K is equal to, so if you can represent this constant value in the graph like this, it will go like a straight and flat line like this. So here you can see in the x-axis we have omega. Maybe I change my pen color again. Everything looks red color here. So x-axis is omega and the y-axis we have the transfer function in terms of dB. So it will be like this. And this is just, you have to remember how can we represent the constant. And phase angle is angle of K is equal to 0 degree when K is greater than 0. Similarly, when K is less than 0, the phase difference is 180 degree. It means minus. K is minus K. Minus K is definitely less than 0. So that is how we can represent. And here you can see, so we are representing this phase angle with this graph. And the magnitude represented like this straight line whenever we have constant. This is how we can construct the Bode plot. This is the case 1. Case 2 is if you have this kind of functions in your output function, or this kind of terms in your output function, 1 divided by s to the power p. So how can we represent the magnitude? Magnitude, so modular of 1 divided by j omega, s is equal to j omega whole power t in terms of dB is equal to minus 20 p, whatever is in the power, we are putting times p times log of omega. So this is how, this is the standard formula whenever you have this term. This is to represent the magnitude. Phase angle is the same, angle of 1 divided by j omega whole power p is equal to minus 90 degree times p, whatever you have in this power. So you have to multiply. If you have 2, for example, s square, then s square means this will be 2, then this will be minus 180 degree. So yes, the p value will not go more than 4 because usually we have maximum 360 degree. Okay, so this is the case 2. If you have this term in the transfer function, then this is the formula to calculate the magnitude and the phase. And the graph will look like this. So this graph will go down in this way. So this is the p equal to 2 and this is the p equal to 1. This is minus 90 degree, this is minus 180 degree. And the phase angle, it's very easy to calculate directly using this formula. And case 3, we have the term s to the power p. Remember the previous one, 1 divided by s to the power p. The case 3, s to the power p. If you have this kind of terms, then how can we calculate? The magnitude is equal to modular of j omega to the power p in terms of dB is equal to 20 times p log omega dB. So here you see here the formula is almost the same. What is the difference between this slide and this slide? Minus. So here we are representing minus and here we don't have any minus. So this is the only difference if you have the term here in the numerator. So 20 times p log omega dB, and this graph will look like this. This is going in the positive side. And similarly, phase angle of j omega to the power p is equal to 90 degree times p. This is the same, minus 90 times p. Here we have minus, here we don't have minus. So this is the standard formula, just remember. And this is the case 4. Case 4 means you may have a divided by s plus a, or 1 divided by a times s plus 1 whole to the power minus 1. Just this is nothing but the same formula. I just write in a different way. Yeah, so the same formula I am writing just in this way. So when you have like this, then how can you represent this, the magnitude? So the magnitude you can represent like this, 1 plus j times omega divided by a whole to the power minus 1 in dB is equal to minus 20 log of square root of 1 plus omega divided by a whole power 2. So this is the way to represent. So of course you can just solve this and then derive this, but we don't need to go into this one. Phase angle is also, this is the formula for the phase angle, 1 plus j times omega divided by a. The same, how can we represent this, is equal to 0 degree minus tan inverse omega by a. So this is the phase angle formula. So here also we have, if omega is less than a, then what is the angle? And if omega is greater than a, you see here, so we have the omega and we have the a. So if omega is greater than a, then what is the formula and what is the angle? So we just apply everything in the formula and you will get this angle value. So now I think we are done with these 4 cases, and I think we have one more case. So that is the case 5. Case 5, this is the formula s plus a divided by a, or we can simply call or rewrite this formula like this: 1 divided by a times s plus 1. So what is the magnitude formula? Magnitude is equal to modular of 1 plus j omega by a in TB is equal to 20 log of square root of 1 plus omega divided by a whole square. This is the formula for magnitude. Or you can also simplify and then rewrite like this, but we will just remember this formula. This is the formula for magnitude calculation, and this is the formula for phase angle calculation. Phase angle of 1 plus j times omega by a is equal to tan inverse omega by a. So in the previous case 4, we have 0 degree minus, right? 0 degree minus tan inverse omega by a. Here just tan inverse omega by a, omega divided by a. And of course you can apply 2 cases here. Omega is much less than a, or omega is much greater than a. So if you apply these values 0 and infinity, then you will get these phase angle values. So whatever these kind of terms you may get in your transfer function, if you have this kind of functions or if this kind of terms in your transfer function, then how can you represent that in your S domain, and how can you calculate the magnitude and phase angle? That is what we had seen in these 5 cases: case 1, 2, 3, 4. This is the case 5. And of course in each case, the phase angle, if you represent in the graph, the phase angle will look like this. The shape will look like this. And similarly here, the case 3, the phase angle will look like this for p equal to 1 and the p equal to 2 and so on. And this is for the case 4, and this is for the case 5. Case 5, this is going towards positive magnitude, and then the phase angle will just start from 0 and then it will raise to 90 degree plus 90 degree, and then after that it will become flat again in 90 degree. The phase angle will not change anymore. It will just be frozen at this point. Okay, so now Bode plot construction. So open loop transfer function, you can always write like this: g of s times h of s. And the closed loop transfer function means, open loop transfer function means, let's say we don't have feedback, and if you have the closed loop transfer function means you have the feedback loop, and then you are representing like this: 1 plus g of s times h of s, and open loop stability poles of g of s times h of s in LHP. So this is LHP means left hand side complex plane, and RHP means right hand side complex plane.